Hello everyone, I am Hariharan Rajasekaran and today I will be talking about the cutting edge innovations in fiber optic sensing. This presentation covers the recent webinars and research works in optical communication and I will walk you through four fascinating topics. The first one is bridge monitoring with distributed fiber optic sensing. This is part of a webinar hosted by FOSA and I will be walking you through the fundamentals of how fiber optics is transforming structural health monitoring. The contents are why bridge monitoring is important and what is distributed fiber optic sensing, how we tested it on bridge models, key results from static measurements, the relationship between displacement and strain, and finally the conclusion. So why bridge monitoring? So why do we need bridge monitoring? Well, many bridges around the world have reached or exceeded their design lifespan. This brings serious safety concerns with monitoring so we can ensure safe operations, move from reactive predictive maintenance, and even extend the lifetime of this critical structure. Distributed fiber optic sensing. Distributed fiber optic sensing or DFOS is revolutionary here. The entire fiber acts as the sensor and enabling distributed strain sensing, distributed temperature sensing, and distributed acoustic sensing. This makes monitoring large structures much more efficient and cost effective. Bridge model lab test. The tested distributed fiber optic sensor in a controlled lab settings. The bridge model was subjected to a single vertical impart followed by a free oscillation. It was mounted with roller bearings on the right and static bearings on the left, simulating real bridge conditions. Static DFOS measurements. Our measurements were based on Boolean frequency domain analysis is or BFODA. They conducted quarterly recordings and also observed data continuously for 2 weeks. Interestingly, they found that temperature changes both daily and seasonally. It plays a huge role in how strain develops over time. Displacement versus strain. Here, the differentiated displacement and strain. Strain was derived from real-time sensing measurements and found to be under 200 microstrain. Although this is small, it is enough to defeat structural changes through the spatial resolution remains relatively coarse. Conclusion. To wrap up, fiber optic sensing is extremely valuable for monitoring both new and existing bridges. It helps localize failure early and is becoming standard in many structural tenders. But remember, calibration is a key to making this technology effective. We'll move on to our next presentation. In this presentation, I will be explaining the merits of a hybrid fluorescent fiber sensor and power over fiber solution for partial discharge detection. This fascinating topic combines photonic sensors and power delivering technologies for high voltage electric systems. And here is a quick overview of what we will be covered in this presentation. A summary of the MHGP product line, details about VMJ photovoltaic cell, what is power over fiber and where power over fiber can be applied, what is partial discharge and how it is detected, and the unique role of fluorescent fiber sensor in PD detection. MHGP product summary. Let's begin with MHGP, a pioneer in advanced photovoltaic power conversion. Their products are mainly used in laser systems, and their suite includes three flagship solutions. This sets the foundation for integrating power and sensing via optical fiber. VMJ PV cell. Next, we have the VMJ PV cell. This high performance silicon based cell is optimized for power over fiber application. It has a remarkable efficiency of uh, around 43% at 976 nanometer and it can deliver over 25 watts per square centimeter. Its high voltage density and low cost design make it ideal for pairing with 9 times the nanometer laser diodes. Background calibration. The VMJ system offers several advantages. Spark-free operation for battery safety and strong noise immunity for signal integrity, voltage isolation for power independence, and it's lightweight, perfect for compact sensor modules in remote or sensitive environments. Power over fiber application. Now let's talk about why we would want to transmit power over fiber. Power over fiber provides a way to deliver power safety and cleanly to systems that are noise sensitive are electrically isolated like sensors or RF or fiber devices. The goal here is to create a hybrid system that combines optical sensing with optical power for partial discharge monitoring. Next, partial discharge description. So, what exactly is partial discharge? It's an electrical spark that occurs across gaps in insulation under high stress. These discharges are usually early signs of insulation breakdown and can eventually cause arc flash or full insulation failure. Detecting PD early is crucial for maintaining safety and reliability. Partial discharge sensors type. There are multiple sensors type available for PD detection in switchgear, but many suffer from limitations like electrical interference or insufficient sensitivity. That's where optical solutions, especially those based on fluorescence, come in. Fluorescence fiber sensor for PD detection. PD eventually emits UV light in the range of 280 to 405 nanometer. Fluorescent fiber sensor are designed to respond to this UV light. They can be tip-based, surface-coated, or even have a doped core. Each setup fluorescence in response to UV emissions, providing a power optical signal. Multifunction sensor module. This fluorescence sensor can be connected to a amplification UV visible sensor module. Key features include UV responsivity between 215 and 365 nanometer, visible responsivity from 500 to 1000 nanometer, and compact dimension, making it easy to deploy. Such modules can even support multiple FFS units at once. Extrinsic sensory, where light exits the fiber. Intrinsic sensor, where interaction happens with the fiber. They can operate using wavelength, phase, or intensity modulation, making them highly adaptable. POF, powered sensor and modulator. The final component of the system in a POF powered sensor that also acts as a modulator. It converts the detected signal, say UV light, from a PD event into an optical signal within the fiber. This hybrid module essentially becomes a self-power compact optical monitoring. Thank you. We'll move on to next to presentation. In this presentation, we will explore about principles and application of single frequency fiber laser strain sensor. This innovative sensing technology has wide ranging uses in precision measurement, acoustic sensing, and advanced imaging. The contents here we what will cover in this presentation: an introduction to the technology, then the operating principle behind it. We will discuss the strain resolution these sensors can achieve, followed by their real-world applications. We will wrap up with the insights into commercial development. Introduction: ultra-sensitive fiber optic displacement sensors are now used in many fields, from infrastructure monitoring to scientific instruments. A special type of sensor, distributed feedback fiber black laser sensor, has proven capable of achieving extremely high displacement resolution. Here's the trick: instead of measuring strain mechanically, these sensors can encode strain data into the frequency of laser, and since thermodynamic noise drops at higher frequencies, these sensors are ideal for precise high frequency measurements. And principle: how does it work? Fiber laser strain sensor uses strain induced modulation of the laser frequency to detect tiny displacements. Each sensor contains a section of doped fiber, specifically germanium, aluminum, erbium doped fiber, along with a fiber backdating that includes a phase shift in its center when strain is applied. The optical cavity length changes, which shifts the laser's frequency. These shifts are measurable with extreme accuracy. Multiple sensors can be written along the same fiber and differentiated by tuning each to a difficult wavelength, enabling multiplexing on a single fiber line. Strain resolution. Here we see the performance results. The black tree in the graph shows measured noise up to 2 MHz. The sensor can detect displacement as small as 10 to the power of minus 16 meters. This corresponds to a strain resolution of just 20 femtostrain. That's 20 into 10 to the power of minus 15 strain, extremely sensitive. Applications. These fiber laser sensors have many advanced applications, including acoustic emission detection, useful in structural monitoring, guided wave acoustic measurement, especially for non-linear propagation, underwater acoustics where electrical systems fail due to corrosion or electromagnetic interference, and photothermal imaging where temperature-induced strain provides image contrast. Their small size and immunity to electromagnetic interference make them ideal for use in extreme environments. Commercial development. Now let's look commercial development. These sensors are written using an excimer laser, and they can be customized in length, usually between 2 and 5 centimeter. In acoustic emission detection tests, they have matched or exceeded the performance of earlier designs. They can be produced either as arrays in a single fiber or as a separate sensing elements that are spliced together using passive fiber. This flexibility masks them scalable and practical for real world deployment. Thank you. We will move on to next presentation. In this presentation, I will be talking about distributed acoustic sensing or DAS using enhanced fibers. Outline. Here's a brief outline of today's talk. I will start with the background on distributed sensing, then I will explain what distributed acoustic sensors, followed by what makes enhanced fibers like ULL and ESR so special. We'll look at how these fibers improve signal to noise ratios, and finally we'll go over some aspects of fiber sensing link design. Background on distributed sensing. Distributed sensing has a broad range of applications including structural health monitoring, perimeter security, oil and gas pipeline monitoring, earthquake distribution, and even asset tracking in telecom networks. What makes distributed sensing unique is that the optical fiber itself becomes a sensor, providing real-time feedback over long distances. Distributed acoustic sensors or DVS. DVS, also known as DVS, stands for Distributed Acoustic Sensing. It uses light scattering in fibers to what's happening at every point on the fiber. What is enhanced backscattering fiber? ASF. Let's now introduce enhanced backscattering fiber or ESF. This is a special type of fiber introduced to reflect more light back forward and the receiver. The particular brand we are discussing here is Acoustic Sense, a fiber for stronger backscatter signals and as a result better sensitivity to acoustic vibrations. ESF attenuation. ESF fibers have optimized attenuation properties. They are engineered to maintain signal strength while maximizing acoustic return. This is a key in ensuring long distance and high resolution measurements. From optical SNR to acoustic SNR, one of the core benefits of ASF is the improvement in signal to noise ratio, or SNR. Higher optical SNR directly translates into more accurate acoustic SNR. This means clearer, more detailed measurements, even more extended length of fibers. Improved phase recovery. Another technical benefit is improved phase recovery. Phase data is critical in DAS applications because it gives you the frequency and location of vibration sources. Enhanced fiber makes it easier to extend phase shifts accurately, which boosts the overall performance of the sensing system. DAS cable with acoustic sense fiber. We also used acoustic sense fibers encased in metal tubes for durability. These cables are rugged, suitable for harsh environments, and can be used in oil fields along railway lines. Is there a telecom penalty in ESF? You might be wondering. Does using ESF impact telecom transmission performance? The good news is no. ESF is designed to work alongside standard communication signals, allowing dual use setups where the same fiber can carry data and sense acoustics. Thank you.